Good afternoon, everybody. Welcome to the 2017 CUAHSI Cyberseminar series on Hillslope hydrology and Earth system models. My name is Liz. I'm the Community Relations Specialist here at CUAHSI. Just wanted to do a housekeeping item. If you are connecting via microphone, we'd like to prefer to have you connect via phone, just because it'll have better audio connection when we have the Q&A session towards the end of each presentation, as well as the overall discussion at the end. So I will pass this off to you now.
Hi, everyone. Welcome again. And as usual, I'm going to run through this intro very, very quickly. For the first-time attendees, and again, this is a 5-series webinar series, 5-part webinar series representing Hillslope hydrology in the large model grid in Earth system models. And it's a CUAHSI NCAR collaboration to engage the hydrologic science community to help figuring out what is the best way to do this. And again, on the lower right panel, this figure that I borrowed from Leho Floors, it shows a large model grid that has plant functional types and a fractional snow cover, but it does not have topographic relief or hillslope hydrology captured by the lower left cartoon that shows there's a elevation difference, the hills to valleys, as well as aspects, the sunny and the shady side of slopes. These we know are critically important in determining the energy and water and carbon fluxes with the atmosphere. And so we have organized a 5-part webinar series to answer these questions. 3 weeks ago, we asked this question: where in the world is hillslope hydrology important to ET over a large ESM model grid? The idea there is to come up with a global framework to understand where hillslope hydrology is really important to the large grid mean vertical fluxes, vertical flux change with the atmosphere, and why. What are the hillslope processes that make them important here? And then the last 2 weeks, we asked the question, what are the basic subgrid units? And if we know where these are important, where hillslope hydrology is important, how do we divide a large ESM grid meaningfully into hydrologically meaningful units? And we had 2 discussions, and here the goal is to come up with some practical approaches, perhaps multiple approaches, to represent drainage, the lateral convergence of water, and the aspect driver in the energy budget, and as well as the water budget. So today we're going to continue to our 4th webinar, asking this question: what are the global data analyses that are needed to partition an ESM grid cell into and parameterize these units as identified in part 2 and part 3? For example, what kind of topographic DEM analysis, geologic, geomorphology, soil, vegetation analysis, variations of these parameters, as well as the covariations along topographic gradients. If we think topography is a strong organizing principle for water and for sedimentation, for plants, etc. So today we have Nate and John to lead the discussion, and our goal again is to figure out a practical way for a global implementation. And so we emphasize this practical way because we are not trying to solve all the world's problems related to hydrology, to heterogeneity. We have a lot of problems to solve, but this project and particularly this webinar series is designed to come up with practical approaches, recommendations to implement hillslope hydrology into ESMs. And then in 2 weeks, we're going to have our last one, which is some kind of summary and synthesis. We'll have Sean Swenson and Dave Lawrence at NCAR to give us an update on what is currently in CLM. And Sean has done a lot of work to prepare CLM to now accommodate hillslope hydrology. And then Martin and I will summarize our efforts in writing the synthesis paper. And with that, I'm going to pass this screen to Nate from Princeton University. Take it away,
Hello.
Nate.
Can you see that, Ying?
Yes. I think Nate is, yeah, now we see it.
Here we go. Good. Hello, all. I'm Nate Chaney, and today what I want to do is talk about harnessing big data to integrate hillslope hydrology into Earth system models. So the motivation behind this work is we have all of this environmental information. We have all this data that we're sitting on, 30 meters, 100 meters, that covers the continental US, covers the globe, etc. And so the question that we have is, how do we use this information? So for elevation, we have over the US, the USGS National Elevation Data Set at 10 meters. We have SRTM plus ASTER at 30 meters over the globe. For soils over the US, we have this Pelletier data set that I developed a couple years back. And we also have soil grids, which was developed by Tom Hengel out of ISRIC at 250 meters. We have land cover information, a lot of it derived from Landsat, so for example, a national land cover database. And we have GlobeLand 30, which was developed for a land cover classification from Landsat. And also we have climate information. So using PRISM from over CONUS, we have 800 meters of 30-year normal precipitation, temperature, etc. As well as for world CLIM, we have 1 kilometer. So we have all of this information. And the question that we ask is, how can we actually use this information to parameterize our subgrid heterogeneity within each macroscale grid cell? And that's really the problem that I've been trying to get out over the past 2 years. And so the background for this work is, I've been working the past couple of years at GFDL with their land model. And this land model is used as a suite of coupled models for Earth system modeling, climate modeling, seasonal prediction, etc. And the main idea is a few years back, Chris Milley developed through LM3 these implicit hill slopes, so you have different characteristic hill slopes within a grid cell. And then in 2014, Zach Subin took these hill slopes and discretized them. So what we have is a characteristic hill slopes, which is discretized into what we're going to call the height bands. And within each height band, we have intra-cluster heterogeneity. So you might have land cover, soil properties, etc. And so each of those characteristic hill slopes will have their own properties. So they might be convergent, divergent, uniform, and they might be convex, concave, etc. And so this is the model that was developed back 3 years ago. But the focus of what I'm going to talk today is not about developing this model or how it works, but it's more around the question of how do you actually parameterize? Because this is actually, in my opinion, an overlooked challenge that we have, which is we have many models, but do we know actually how to take the information that's available to us from global data sets to actually parameterize them? So 3 questions I want to try to get at are, what are the characteristic hill slopes for each grid cell? How many height bands do we need for each of these hill slopes? And how do we define the intra-band tau heterogeneity? So as an example, I just chose a quarter grid cell for the foothills of Sierra Nevada. And you could choose any grid cell that has a lot of heterogeneity. I chose this one because you can see a lot of heterogeneity in topography, in soils, in land cover, in precipitation, etc. So you can think about it as representative exploring this idea. So if you look at this at 30 meters, look at all this data that we have, it's around 1 million 30-meter grid cells. And so what I aim to do is to figure out a way to take all of these proxies of heterogeneity, all this information which we know is related to the actual processes, extract as much information from this data as possible, and then put them through a clustering algorithm to extract the representative tiles. So here is an easy example. You have one characteristic hill slope, and you have 4 band height bands, and you have one interclustered tile. And so you take this model, you take these tiles, you put them into your model with hill slopes, you have your meteorology, and then you have your tile simulations for each of the tiles. And because we have water converging down to the riparian zone, you're going to have a higher ET signal happening in that region, as you would expect. One of the consequences of doing this is when you have these 4 tiles or n tiles, and you have these different time series for each one, you also have this map. So in clustering this information, you've created a 30-meter mapping of the clusters in space. So you can actually take a time step. So here it's a day in May of 2002. Just take the values for the 4 clusters or tiles and just map them out. So here's the evaporation that you have coming from the model, and you also have the corresponding soil temperatures. So in the areas of higher topographic convergence, you have more water, so the soil temperature is lower. You have the runoff, which is occurring close to the channel, and you have the higher leaf area index because you have more water available to you. So all these are prognostic variables. So that's a very simple way of understanding how we're trying to cluster this information to include it within our models. But what I want to do is take a few minutes to dive into some details of how we actually do this hierarchical clustering. So I want to define the characteristic hill slopes, discretize the characteristic hill slopes into height bands, and then define that intra-band heterogeneity. So how I do this is first just start off with elevation map. So here's the elevation map for that quarter-degree grid cell at 30 meters. And you just delineate the channels, and with those channels then you delineate the hill slopes. And once you have those hill slopes, you have all this environmental information, which you can then come along and then just compute some average properties or characteristic properties for each of those hill slopes. This is before actually coming up with the characteristic hill slopes. So you might have a mean slope for the hill slope, you have a mean aspect, a mean length, a mean precipitation, mean temperature. And also you want to learn something about its geometry. So you can actually take the height above nearest drainage and fit a width function. So going from the channel up to the ridge, how does the width of the hill slope change? And you can do the same thing with the slope. So those two, one is going to give you information if it's convergent or divergent. The other one's going to give you information if it's concave or convex. Right, so you have all these properties related to your hill slopes. So you take these properties, put them into a clustering algorithm, in this case k-means, and it's going to give us these characteristic hill slopes. So here I've chosen an example, k equals 10. So you can see the areas in the uplands where you have 2 characteristic hill slopes. You have going down to the valley, you have other characteristic hill slopes, and then you have ones in the central valley. So you see this distinction that's happened just because of these drivers of heterogeneity that you're feeding into the clustering algorithm. So then the next one is to discretize these characteristic hill slopes. So we have these 10 characteristic hill slopes, or the user-defined K, and we need to divide them into these columns or height bands. And so what we do is we take a function which we fitted for each of these characteristic hill slopes, and we just discretize it. And we discretize it by specifying a delta H, which is the difference in elevation between 2 adjacent height bands. And so you can see that because the length of each hill slope that we've clustered on will be, in most cases, will be different, and the total height will be different as well, the maximum height, you're going to have a different number of bands per characteristic hill slope. So here's just the case where you take the map of height above nearest drainage, you take the map of characteristic hill slopes, and without going into too much detail, you can then just do a mapping for each 30-meter grid cell. You calculate the hand for each grid cell, you know the characteristic hill slope that it belongs to, so you can assign it to a unique band. And so here I'm showing which L equals 61, so that's the total number of these unique clusters for this quarter-degree grid cell. So the last step is then to define the intra-band heterogeneity. So these intra-band clusters. So you have these characteristic hill slopes and you have these height bands. And now we want to say something about the heterogeneity within the band itself. Because in rare situations are you going to have the same porosity, land cover, etc. within each band. And so this is just, you take each unique band, and with each of those bands independently, you run k-means with the corresponding properties. And so here, P is the number of clusters for each of those bands. I set P to equal to 3. And here's the case where then you have all of the tiles for that entire quarter-V grid cell. And so here's just a way of computing, or the parameters that then go into this algorithm. So number of characteristic hill slope, which is K, delta H, which is the height difference between adjacent bands, and P, which is the number of intra-band clusters per band per hill slope. So that's a lot of detail, but the main idea I want to get across is we have all these proxies of heterogeneity. We have this, we're going to call a hierarchical clustering algorithm. And that clustering algorithm takes into account all this heterogeneity and uses hill slope structure to actually get the hill slope structure correct in our model, and then puts it into our model. Now, I should note here, the model is not actually seeing a map of tiles. The model is only seeing, as classical land models, they're just seeing n tiles, and that n in this case I think is 183. So it has 183 different tiles, where each tile has a unique set of properties, and it can have its actually unique meteorology. So here I actually superimposed 4-kilometer Princeton CONUS forcing data set, which is derived from stage 4 and NLDAS. So you actually have a meteorology for each tile, and then the interconnections between those tiles, which is driven by the hill slope. So the main point is that you have 1 million 30-meter grid cells, which are reducing down to about 10 to 1,000 tiles. So I just want to show some model simulations that you get when doing this. So what I want to do is actually play around with those parameters, the K, the delta H, and the P, to help understand how effectively playing with the characteristic hill slopes, the number of columns, or the number of intra-band clusters impacts the heterogeneity of the system. So there's some simulations between 2002 and 2014 with a spin up between 74 and 2001. And I'm showing on the right some tile configuration, the massive tile configurations for these different setups, where the n tiles equals 1, you'll be your homogeneous grid cell, and in this case, the most heterogeneous one would be the number of tiles equals 1585. So what I'm showing here is running it with these different configurations. As I discussed previously, because we have a time series for each of these tiles and we have a map for each of the tiles at 30 meters, we can compute, for example, the annual mean runoff between 2002 and 2014 and just map it out. And so here's the mapped out for the annual mean runoff, and we're playing with each of these different parameters. So when you go from 1 to 7, you're immediately adding these elevation bands, these band heights, when you can actually see then convergence happening in the runoff, so you have the runoff being produced at the channel. Then when you add these intra-band clusters, so you're playing with P, then you're adding some heterogeneity in terms of land cover and soil properties. The biggest difference in runoff then happens when you start increasing the number of characteristic hill slopes, where you're really starting to capture the impact of orography in terms of precipitation and the hill slope structure. But if you look at this closely, what you end up seeing is that after a certain point, the change of your map is actually very small. And you can actually formalize this and just plot here the spatial mean, so take each of those maps, compute the actual average, and then plot it against the number of tiles. And I color-coded it to see the parameters that I'm changing. So green, I'm changing the number of height bands. Red, I'm changing the number of intra-band clusters. And blue, I'm changing the number of characteristic hill slopes. So for runoff, the biggest driver in terms of changing that runoff from the homogeneous case is when you're going from 2 to 5 characteristic hill slopes. Now this is specific to this grid cell, and this will be different for in other places. But the point is that these different drivers play a different role. And the exciting thing is that by the time you hit 200 tiles, you're really converging on a solution, and you're not really changing that much, both the spatial mean and the spatial standard deviation. So there is a point in which we don't need to keep adding more and more heterogeneity to our system, and from a macro scale perspective, we're going to be getting a fairly similar answer. So here's adding that and doing all with the other variables that are available as prognostic variables for the model, where I showed runoff. As expected, evapotranspiration is effectively the flipped version of runoff, because really what's happening there is increasing the number of characteristic hill slopes is just changing your precipitation partitioning. And all those two are driven by the number of characteristic hill slopes. But that is not the case for leaf area index, where the biggest difference or the biggest driver is the number of intra-band clusters, which is the same case for sensible heat and soil temperature. While for soil moisture, as you can see, the biggest change happens when you go from the number of bands equals to 1, so the homogeneous case down to up to 7, which is not surprising. From a topographic index perspective, you know that when you have topographic convergence, you're going to have the soil moisture is going to be higher in those regions, so you'd expect the biggest driver to be the fact of adding in these bands. So the fact that multiple ones, so they're driven by multiple drivers, but also the encouraging thing that the spatial mean in pretty much all these cases, actually in all these cases, converges very closely when you hit the 200 tiles. So for this case, you don't even need to go to above 200 tiles to effectively get the same spatial mean for the macro scale. So just a couple of minutes before I wrap this up. So here are just a few more examples of these mapped simulations for these different variables. And I added 5 prognostic variables, but I also added precipitation. Precipitation is not a prognostic variable. In this case, it's an input into the model. But I wanted to show it because, as I said, I superimposed a 4-kilometer grid on top, the meteorology, and I assigned, effectively, knowing the 30-meter mapping, I can then assign the meteorology for each tile. And then you map that out, and you look at the annual mean precipitation, you can see that very sharp gradient that's occurring in the inputs. And that's a big driver when you look at the different prognostic variables of actual heterogeneity in the system. So what I learned from that, and I think is something important to bring up, is that as we worry about the hill slope hydrology, it's important to make sure that we're getting the land right, but at the end of the day, we can't run away from the problem of we have to include some way to effectively downscale information, whether it be temperature, specific humidity, et cetera, within the grid cell, because these microclimates are going to play a large role in this heterogeneity problem. So just to finish up, so what I showed here is an example in California. A couple months back, we actually took this hierarchical clustering algorithm and we just ran it over the entire US. So we divided the US into quarter-degree grid, where for each quarter-degree grid, we computed 100 tiles using the algorithm that I discussed previously. So you add that up, that's around roughly 1.5 million different tiles over CONUS, where each 30-meter grid cell belongs to a tile. You simulate between 2002 and 2014 with a spin up to between 74 and 2001. So here is that same idea, the tile mapping for each quarter-degree grid cell, where you can see the different sources of heterogeneity. In the one on the upper right, you're seeing actually urban areas that are popping up because you're actually clustering on that. In other areas, you actually have farmlands that are being clustered, which is coming directly from Landsat. So what I want to show here is then, we did this, and this is the simulated leaf area index, and these are the mapped out leaf area index for July 2002. And I just want to show this one. So you see the one in California, where you can see clearly the role of aspect in terms of north-facing, south-facing hill slopes. We have to be careful here, though, because in doing the intra-band clusters, what I'm doing here is I'm effectively clustering on land cover information. So I'm effectively telling that tile that it is an evergreen forest, while the other one on the other side of the hill slope, I'm telling it it's a grassland, right? So this is not getting at the problem yet of here are all these potential ones that could grow here. Which one is the one that actually excels given the environmental information? However, you could include that within this setup. So just to wrap it up, the main purpose of what I'm trying to get at with this problem is try to figure out how we can harness big data within land surface models. We have all this information that we're sitting on, 30 meters, 100 meters over the globe. And what I've developed is this clustering algorithm that is fairly generalizable and you can apply at a continental to global scale to come up with these tiles, which you can feed into these land models, and then you can actually map out to produce these 30-meter estimates. And the main point of this is then to improve the representation of subgrid heterogeneity while ensuring computational efficiency so this can be used for ESMs. And with that, thanks so much. I'll turn the time back over to Ying and Liz, and I'm happy to take any questions.
If you have any questions, please type it into the chat box or raise your hand, and we will unmute you.
Thank you so much, Nate. This is fantastic. what you presented really spoke to several of the issues we discussed throughout this webinar series. And I have really, this is the first time I'm, really looking at this. So there's a lot of information, a lot of details. So just one technical question. What do you mean by clustering? How do you cluster? You have all these layers of information. What do you mean by that?
So k-means clustering is effectively, so let's take the hill slope case. So we have, in this case, you might have like 6,000 hill slopes for that grid cell. And then I compute the average properties for each of those hill slopes. So I have an n by m array, and that n is the number of hill slopes, and m is the number of properties. And effectively clustering, what it's doing is its k-means is just effectively trying to group them in so that their means, the mean of the cluster, is effectively, it groups them as close together as possible. So it's taking all these drivers of heterogeneity and it's just trying to figure out which ones are closer to each other.
So in theory, you have an n space, and so you can imagine this cloud, this n-dimensional cloud. Your data is everywhere, and so you are actually in this n-dimensional space, you have those clusters of clouds, I suppose. Yes. And then this is how you decide this will become one category, and you're going to deal with that explicitly, simulating the fluxes. Yeah.
So in a previous version of this work, so HydroBlocks, which I developed around 2 years ago, in that case I just threw everything at k-means. And then even accumulation area. The problem with that is the hydrology, you're not accounting for the hydrology necessarily explicitly. What we're doing here is, because we have this hierarchical clustering, I'm ensuring that the hill slopes actually make sense from a physical physical perspective. So you're maintaining the hydrology consistent with what you'd expect, and what you're clustering is actually fairly unique properties that tell you something about the hydrology and something about the system, but they can be clustered in this way.
So how do you deal with then the lateral movement of water among the clusters?
Right. So as I pointed out, so there's these three hierarchies, there's three levels of the clustering. So the first thing that I do is I cluster the hill slopes.
Right.
And so by clustering the hill slopes, I come with these 10 characteristic hill slopes. So those 10 characteristic hill slopes, each of those is going to have its own width function. It's going to have its own relief function, etc. And then it's going to discretize it. So each of those bands, which we're going to talk about, they're all interconnected. So when I create the mapping between 30-meter data and the actual hill slope clusters, I ensure that it's a one-to-one connection. Now, this is the case where you can have two hill slopes in the landscape that are not close to each other, right? And from a physical perspective, but from their physical properties, they're very similar, so their physical hydrologic response ends up being identical. So what we're saying here is that two hill slopes that are not necessarily next to each other, but are in the landscape, their properties are so similar that they effectively behave the same way, so the output from the model for those two hill slopes is the same.
Okay, then how do you map it back? If you have those representative hill slopes, like 10 types, right, according to your plan profile and the curvature and the profile and the plan curvature, how do you then map back into in your results when you show the ET, when you show the runoff? They're spatially explicit.
Yep. So if you see this right here, so here's the characteristic hill slopes, right, that I've mapped out. So each of those hill slopes that I have now belongs to one of those characteristic hill slopes I. So then what I do is I take this height above nearest drainage, and effectively I then partition each of those 30-meter grid cells. So I know which characteristic hill slope the 30-meter grid cell belongs to, and I know the hand, and so I immediately know the band that it belongs to, right? And so by doing that and then adding in the intra-band clusters, then what happens is I have this map of tiles, right? And so this map of tiles with all these colors here, there's a lot of heterogeneity, but really all that's there is just 100, in this case, 183 tiles. And each of those tiles has their own properties, and they're all interconnected, well, within the hill slope. Yeah.
Okay. Thank you.
So we have quite a few questions. I don't know if you want to take one or two and then move on.
Yeah, let's read them. Let's let them ask these questions.
Okay, so Xingwan Chen asked, do you consider the correlation between different data types?
Right, so currently no. So currently when I do the clustering, all that I do is I normalize it, and then I effectively assume that each of them has the equal weight. I actually have been playing around with this problem because what happens is if I throw precipitation as a covariate and then I throw a bunch of other elevation derived products, the elevation might effectively it'll just outweigh the rest of them, and it might actually wipe out the precipitation signal. So that does happen. So what I've been playing around recently is with actually a convergence algorithm playing with the weights, and you actually remove the correlation. I've also played around with PCA with this, but the results that I got were not that different. But that's some place. I think the decorrelating these data is an area that needs to be explored more. I agree with that.
Okay, the next question is from Stephen Kramer. He says, great presentation, practical approach for spatial heterogeneity. How about temporal variability of forcings like precip?
Right, so the way that we set this up is it can be run offline or online. Because they're set up here at GFDL, it's made to be coupled. So in this case, what I showed here was an offline simulation where I have this CONUS forcing data set at 4 kilometers. It's an hourly product over the US between 2002 and 2014. And what I do is, if you imagine for each grid cell, you have this 30-meter mapping, right? So each 30-meter grid cell belongs to a tile. And so what I can do is come along with this 4-kilometer grid of the meteorology, and I can effectively do a mapping, and I can figure out the meteorology that corresponds to that tile. Because I've included orography in doing this, that's how you get the heterogeneity in, for example, precipitation inside of it.
All right, next question is from Steve Burgess. How do you represent convective rainfall or atmospheric rivers?
So the short answer is it really depends on, I think, the application. So one of the covariates that you can use as well in the Hillslope clustering is actually latitude, longitude. So if you include latitude, longitude as a cluster, you're actually approximating what would be a subgrid within the grid cell itself. And so that way, if you have very fine resolution rainfall, you can account for it. But I think the question of how do I account for heterogeneity, it really depends on the application. So if the application of this is for very short-term flood forecasting, then the number of tiles you'll need will increase dramatically. But if what you're interested in is like daily estimates, then you'll have a lot of smoothing in terms of the rainfall. So you need to account for the orography, but not as much as you would if you're doing very fine time scales.
All right, next question is from Zhu Liang. Does each of your clusters vary with time, as some properties are time invariant? Example, slope. Will others like temperature, precipitation vary with time? If yes, how do you account for it?
So within the clustering, the temperature and precipitation that I used, all that I used was a 30-meter mean. So from WorldClim and Prism, I just used a 30-year mean of precip and temperature just to get an idea of the impact or the orography on the heterogeneity problem. You can let these things vary over time. So at GFDL, we actually have ways to partition and merge tiles, but there has to be a parent tile, which is the way that I put it, and that's going to be driven by what you are going to assume for the time being are static covariates. So we're going to assume the elevation for our purposes is going to be static, for example. But yeah, as climate varies, you're going to have to update those, right? That's for sure.
There are tons of questions out there for you.
Go ahead, Liz. Let's quickly go through this.
All right, Dave Tarbon, what definition of streams did you use for hand? Second question, what are your hill slopes? One of the slides looked like opposite sides of a stream were the same hill slope, suggesting sub-watersheds perhaps.
Yeah, so the current way that I do the hill slopes is, let me go back here. All that I'm really doing is I'm taking a sub-basin and turning it into a left-hand side, a right-hand side, and a headwater. So that's fairly similar to what Huri is doing in terms of how we capture it. However, if there are better ways to yet I got the hill slopes, I'm all up for that. And any suggestions?
Okay, next one's Anderson Ward. He says, you've looked at elevation, slope, KSAT, temp, etc. One of the biggest problems I've had is estimating spatially variable soil thickness. Any suggestions?
So I think I'll leave this one to John, the next presenter. I completely agree that soil thickness is extremely important, depth of bedrock, etc. And although I'm not including that right now, you can think about, you could compute the average soil thickness for the hill slope, or you could do the soil thickness for the intra-band clustering. But you could include that information within the clustering itself, which would then be passed along into the properties for the tile.
All right, next question is from Solomon Vimal. When you say that 183 tiles are connected, it's not clear how they are connected. Can you explain that a bit more? And how do you set the accumulation threshold for hand?
You know, this question maybe will hold a little bit. This is a little more technical, and we need to move on to the next. Can we come back to this, Solomon, please? Thank you.
All right, so we'll move on to the next presenter.
Yes. I mean, one more question, very quick. What is your preferred method of clustering? Like Euclidean cluster, how do you deal with nonlinearity in the data sets?
So currently I am using the Euclidean clusters. So the ways in terms I'm dealing with the nonlinearities, I'm really not accounting them for right now, and that's definitely an unresolved challenge. But I have seen cases in which if there are dramatic outliers, it can really play a massive role. However, do you want to remove the outliers? Because the outliers might be some interesting hydrologies happening there as well. So it's kind of hard what you choose to do there. But I'm all up for other suggestions on how to do the clustering as well.
Ned, do you have a quick answer to Solomon's question? When you say the 183 tiles are connected, it's not clear how they are connected. Can you explain that a bit more? And how do you set the accumulation threshold for hand?
So this goes back to this one right here. So you have the hill slopes, right? So I know these hill slopes, so the characteristic hill slope is unique, right? And so each of these hill slopes then belong to this characteristic hill slopes. So not all of the 183 tiles are connected. What are connected are all of the tiles that belong to a characteristic hill slope, right? So in this case, I have 10 characteristic hill slopes. So all tiles that belong to characteristic hill slope I will be connected. One might be up on the ridge, one might be down the channel, but they're interconnected from a hydrologic sense. This all ends at the channel, right? So currently there's not a way to connect the hill slopes. There's not necessarily a groundwater model. These hill slopes are independent units, right? And that's something that needs to be addressed, especially when you go to flatlands, which in that case, we just revert to a hill slope that has one height band and the heterogeneity is driven by the intra-band cluster.
There is a hand raised by Anderson Ward, and Anderson, can we wait? We need to move to the next speaker. Thank you, and please remember to raise your hand again. Let's move to John. Thank you so much, Nate. We'll have some time to discuss this more. And someone raised a question about soil depth, and John will specifically speak to that.
So I'm trying to show my screen.
Yeah, we see it.
You do? Okay, excellent. All right, so yeah, I want to thank Ying and Liz for their leadership and logistical support for this series, and for inviting me to share a few thoughts. So I'd like to begin with the question of how we characterize the subsurface architecture of the critical zone, essentially globally, at a resolution that resolves individual hill slopes. So, you know, ideally what we want is a map, three-dimensional map, that includes variations as a function of depth in porosity, permeability, and also in other soil hydrologic parameters that honors geology, and that gets to the question that Nate was asked about, you know, about soil depth and depth to bedrock. So there have been a couple of papers. I'm going to use this question as a motivating example that I think highlights some of the approaches that have been taken recently. And then I'm going to broaden it out somewhat to talk a bit more broadly about geomorphology and some of the things that we want to characterize at the hill slope scale and for ESMs. So in this first slide here, I'm just going to highlight a couple of papers that were published last year. So in a paper that I wrote with colleagues at the U of A in James 2016, provided global 1 kilometer gridded data sets for soil thickness. And these were based on topography and climate relationships, and also the depth to unweathered bedrock, so fresh bedrock with very low porosity. And that was based on a control from permanent water table. So I'll discuss this in a bit more detail. I want to emphasize here that this analysis differentiated between uplands, which are essentially mountain ranges. These are areas where the depth to bedrock is tens of meters typically, and lowlands where there are relatively thick sedimentary deposits where the unconsolidated material above bedrock can be tens of meters to, in some cases, kilometers. And so those differentiations between uplands and lowlands, and we also differentiated between hill slopes and valley bottoms, because valley bottoms can have significantly thicker deposits even in upland environments. So upland environments have experienced climate changes that have given rise to fairly thick fluvial deposits along the valley bottoms. And so we've attempted to essentially break up the world at 90 meter per pixel resolution into uplands and lowlands, and also between hill slopes and valley bottoms. And some of that work is relevant here. Second of all, there was a paper published later in the year that provided, again, a global 1 kilometer, what I would call a depth to driller's bedrock. And so in this case, driller's bedrock, meaning this is what a local driller would recognize as the hard stuff. So still, so highly weathered bedrock in some cases, but material that is no longer the unconsolidated overburden above bedrock. And they took a neural network approach that was very different. So the Pelletier approach was a bit more theoretically based with a small number of parameters. The neural network approach has thousands or tens of thousands of degrees of freedom, the way it was applied by these authors. And I think the pro of that approach is that they were able to do an exceptionally good job at reproducing or characterizing the spatial variability of depth to bedrock in places where the input data is very dense. So their approach was able to, in places like Pennsylvania, where there are tens of thousands of data points, they were able to reproduce that input data very well. In other places, parts of the world, where there's very little data to train the algorithm, then I had some more questions about the accuracy of what they were able to do. But in any case, these are two recent approaches to try to characterize the subsurface. So in the second slide, I just want to show a conceptual model for what an upland hill slope to valley bottom transect might look like. And so this is essentially the conceptual model that we used in this recent paper. We were trying to identify the depth of unconsolidated material, which on hill slopes, so up high in the topography near the ridge lines, you're really talking about up to about 3 meters of soil, typically. Beneath that is what we call intact or immobile regolith. This is weathered, fractured bedrock that can contain substantial water that can be tapped during droughts and is very important for trees during droughts, and can be tens of meters and often is tens of meters. And then below that is what we'd call a fresh, unweathered bedrock. So bedrock that is, unless it's highly fractured, is typically just a few percent in terms of porosity. Now, down at the bottom of the slope, you have again the unconsolidated thickness of sedimentary deposits can become quite thick. It can be tens of meters. So that soil effectively, or unconsolidated material, thickens up substantially. So it makes sense within this conceptual framework that we would try to identify both hill slopes and valley bottoms, and also uplands, which is where this conceptual model applies, and lowlands, where you don't have any regolith at all and you really just have thick unconsolidated deposits above bedrock. Now, in this particular study, we tried to identify discrete layers and the thicknesses of those layers and how they vary across the globe. One could also, at the very outset, say, well, wouldn't it be better to try to identify the functions that represent, say, a continuous, semi-continuous depth variation in an actual soil property like porosity, right? So I'll come back to that question again a little bit later, but in this particular approach, we're just trying to identify what these layers were so that they could be implemented in CLM and other Earth system models. So just to give you a sense of some of the geologic data that are being brought to bear here, basically when we're doing upland versus lowlands, we're really trying to get at, map essentially where there is bedrock within a few tens of meters from the surface around the globe. And so we need geologic map data to do that, and those data are not perfect, of course. In general, pre-Cenozoic bedrock, these represent areas that are well characterized as uplands, as areas that have relatively thin soil and regolith above bedrock, and areas that have not been glaciated. So areas that are glaciated within the Quaternary have typically tens of meters to maybe a little bit more of glacial till and other kinds of drift that dominate the subsurface architecture. So in the lower right corner, I'm just showing the maps of superficial deposits from the Laurentide ice sheet as an example. And then over on the left-hand corner, I'm just looking at different ages of superficial deposits. And so when doing this kind of work, you're using the best available geologic data from areas that have not been particularly well mapped around the world, South America, Africa, Middle East being particularly good examples where we have different kinds of mapping that's been done. And so that introduces some uncertainty. And so we're always looking for better geologic map data and better usage of those geologic maps. But we have pretty one can look at the details of this particular paper to see how we broke down the ages of different bedrock geologic units to try to ascertain what is unconsolidated and what is not. And we made, the best choices that we could at the time. Now, as part of that work, again, as I noted, we wanted to characterize hill slopes and valleys. And so this analysis was done, and a number of analyses were done at the highest resolution available, which is basically 90 meter per pixel global SRTM analysis. So what I'm doing here is I'm showing how one can extract hill slopes and valleys, and I'm just showing two of the roughly several thousand global 1 degree by 1 degree tiles. So in this type of approach, we're taking the SRTM data, and this is done in a parallel way on a high-performance computing system where each 1 degree by 1 degree tile is analyzed. And I'm using a particular algorithm that I developed in 2012 to extract hill slopes and valleys. And this algorithm makes a distinction between first-order hill slopes and second-order hill slopes for the purposes of feeding into the work that Peter Heisenberg discussed a couple weeks ago. But one can break out, a hierarchy of hill slope types depending upon how many upstream tributaries they have and that sort of thing. So just showing on the top here, I'm showing an example from the Great Plains, and on the bottom, I'm showing an example from Southern California, basin and range style topography with distributary drainage. And the point here is just to make the point that it has been discussed, and the issue of drainage density has come up in the previous discussions, and so as a byproduct of the analysis that we did in 2016, we have a global map of drainage density at 90 meter resolution, and it may not be the only map or the best map out there, but it's one that is available. And so for the purposes of mapping soil thickness around the world, we just took the area within each 1 kilometer grid cell using this higher resolution analysis in order to have essentially a fraction of hill slope versus a fraction of valley bottom. So we extracted this data in a very simple way just to figure out the percentage of area represented by hill slopes versus valley bottoms, and thereby to develop a tile type of approach based upon how much area is valley bottom versus how much area is hill slope. But one could imagine using these data in a lot of different ways. So I just want to emphasize here that there is a technology that's been developed and that I'm happy to share that does this 1 degree by 1 degree analysis in parallel. So if you have analysis that you want to do on every one of the land tiles around the world, it can be done with many workers working at the same time and returning that analysis all at once. and aggregating that analysis as needed. So one of the questions that Ying posed was, what are the terrain features to pull out of high-res DEMs and other global databases to derive parameters for hill slope models in CLM? And so here I this is a partial list of the derivative global products. So derivative meaning this is not exactly what we presented in this paper, but these are things that we computed as byproducts of the analysis, and they include drainage density, the statistical moments of hill slope gradient and aspect, hill slope width functions, and so Nate has also spoken to many of these issues as well. And also we were interested, we also calculated the channel width versus stage. So just as again, as a byproduct, if we're interested in doing, if we're interested in modeling flood waves through systems using state-dependent friction values, then we need to know the wetted perimeter as a function of the flood stage, and we need to know that globally at high resolution. So that's been done, and I'd be happy to follow up on those. So these are things that I've been hoping to get out since this paper, but I haven't quite had the time to do it, and I just wanted to advertise it briefly that some of these, that part of the synthesis paper could describe the kinds of techniques that are being used to create these high-resolution global maps. So just to come back to the issue of soil thickness and regolith thickness briefly, this is data for the conterminous US, which was used as the calibration data set for this particular paper. And on the independent x-axis, this is hill slope curvature. So as curvature increases, and this is a Laplacian curvature, you are decreasing your soil thickness, high mountain areas, high relief areas, the soils get thinner. And then also there's a relationship with mean annual rainfall. In this particular case was the variable that I was using to characterize thicker versus thinner soils for a given topography. Now, one could argue that vegetation might be a better independent variable in this case, or other kinds of combinations of climate. This is the one that we used in this particular case, and we're revisiting this for version 2 of that data set. Now, there are other soil data sets that are available. Certainly, the Harmonized Soil Database of the World is sort of the go-to data set, and there are rasterized versions of that polygonal data set. But this is a product that uses local high-resolution topographic data at 90-meter resolution, together with this empirical correlation between topography and climate and soil thickness to make a prediction. Okay, so it does, each individual grid point has an independent value as opposed to a rasterized polygon of, say, all of Afghanistan, which is a single value, right? So that's the alternative that's available. We're trying to improve upon that, and this was a first attempt, and so there was some success here, but also some room for improvement. This is just an example of the validation of the data set to Europe, and the European Soils Database comes in thickness classes, 0 to 40 centimeters, 40 to 80 centimeters, etc. And so the observed and predicted is compared here, and there's a bit more detail in the pub paper if you want to read about those. We're also interested, again, in getting at the deep subsurface architecture. So knowing that trees can tap this intact regolith, which in many cases has porosity values that are, between 5 and 15%, and extends down for tens of meters. We were interested in characterizing that. So the conceptual model for how this intact regolith works, this is an evolving field, but Rempe and Dietrich a couple years ago came up with a model that was based on the depth to the permanent water table. And so they were trying to identify, the motivation in part for this particular model was the fact that the depth to bedrock, depth to fresh bedrock, is generally quite low, very thin in valley bottoms, which are wet and perennially wet. And then up high in the ridge tops, where there's much more variation, and where the water table tends to be lower, these are areas where that depth to regolith generally increases substantially to 20, 30, 40 meters in some cases. And it may also depend on the state of topographic stress and tectonic stress. And so, again, this is not necessarily the only control, but what I did was I took the data from Ying Fang's work on depth to perennial water table to create a map of the upland regolith, the upland hill slope regolith thickness. So this is just a map that's only for the uplands, So it shows all mountainous areas. In the lower figure, you're looking at essentially all the mountainous areas of the western United States, and you're looking at the broad Appalachians and the Piedmont region. And so we're looking essentially at a few tens of meters at the deepest. So this was an attempt to describe the total thickness of the critical zone globally at an appropriate resolution. So I just want to take a step backward. Since we've had time to move on and work on other things and then come back to this problem, I'm also working now on an attempt to take a more continuous approach. So rather than just describing these things as discrete layers, I've been working now to take some of the same original work. Certainly, we're using a lot of the same approaches for using the geology and the glacial cover and things like that, the maps of superficial deposits. Those are not going to change. But what I've begun to do is to take data for porosity as a function of depth, both in sedimentary basins and also in uplands based on shallow seismic liquefaction surveys that have been run, and trying to characterize porosity and other soil hydrologic parameters as a function of depth using characteristic functions. And so those functions are basically two parameter functions, and one can imagine what they might be: exponentials, power laws, things like that. And in many cases there is a large degree of similarity in the functions and the parameters, those two parameters that characterize spatial variability and also the value at the surface. Those values vary, but the functions themselves are fairly universal, I'm finding, which is a positive thing. So trying to now characterize the spatial variability in the actual variables that we want as a function of depth in a more continuous way that I think that may be easier for Earth system models to work with. So I'll leave it there, and I hope that my talk has stimulated a few questions that I can answer.
All right, if you have any questions, please type it into the chat box.
John, do you have the global bedrock depth map at 1 kilometer or 30 arcsecond resolution? Can you put that on the screen if you have it ready?
I'm sorry, I don't have it.
Okay.
Yeah.
And these two talks are complementary in many ways. And Nate, using his hierarchical clustering method, brought in basically everything we can observe from the surface. And John has just brought in the subsurface and geology. This is such a black box. We know so little, and I think this data set that John developed and still improving, will be a huge asset that in the future that perhaps can be integrated with Nate's clustering and classification scheme. But the resolution may not agree. Nate is looking at 30 meter. And John, your data set right now is a 30 arcsecond, which is about a kilometer, correct?
Yeah, that's true. So I do think that there is a potential to go to 90 meter and 30 meter. So in the data set that we proposed, there was some aggregation again of the. So certainly we're resolving, as I showed in one of the slides, we're certainly resolving hill slopes and valley bottoms at hill slope resolution, at 90 meter resolution. And there was some aggregation of those data to get to characterize the soil thickness on hill slopes, and then also the soil thickness or the sedimentary deposit thickness in valley bottoms. And then we're thinking about a tile approach where 1 kilometer or 30 arcsecond would be the maximum resolution. But if Nate is now working easily at 30 meter resolution, then I think that gives us motivation for keeping all of the analysis that we can do at the highest possible resolution. And that's not a challenge in the sense that we're already doing a lot of aggregation of analyses that are done at 90-meter resolution and could theoretically be done at slightly higher resolution. So, yeah, I think that's a motivation for us to go to a higher resulation.
In many parts of the world, it's not necessary, but in the very high relief terrain and high resolution would make sense. It's really a practical consideration. How do we combine those approaches and then come up with a more comprehensive way of tiling the grid? So there are some other question. There is, from Anderson Ward, and he wrote this question down. And let me know if you would like to speak, and we can unmute you. Anderson wrote, I've been working water balance on small islands in the Caribbean, some 20 kilometers at their longest points. Any recommendation for downscaling soil thickness to less than the 1 kilometer global models? I think this question is for John.
Yeah. So I guess so we began at the higher resolution. So the original paper. So there's been a fairly long history going back 10 or 20 years of geomorphologists trying to use a combination of trying to use equations that have been developed, and essentially there are two parts to the soil production erosion equation. The first part is soil production itself, which is an exponential function. Typically, it's assumed to be an exponential function. There's good data to support this as a function of soil thickness. So essentially, as the soil thickens, it develops a buffer from weathering agents like freeze-thaw activity and infiltrating waters and things like that, such that the rate of soil production, the rate at which regolith is converted into soil decreases as the soil buffer increases in thickness. And so you can take that, you can combine it with a soil transport function, which is a function of slope and or curvature, and those models can be applied at 30-meter resolution, and that's been done. That was done first. So one paper is Pelletier and Rasmussen, WR 2009. There are other papers out there. I'm just mentioning the one that I know best because it's my paper. But that paper was applied. So essentially, you go out and dig a bunch of soil pits in the field at a watershed scale, and then you use those to calibrate this type of theoretical model that I described, which has a production and an erosion component, and then in a steady state, assuming a steady state, one can map spatial variability and calibrate the parameters of that model, which are just like parameters of that model, and across the landscape. So one can use the use your in-situ data, whatever that is, whether that's basically it's someone going out and measuring soil thickness across the landscape. And it can be you, or it can be the local soil conservation service, or whatever. So that can be done for sure at so if you're doing a fairly small area, small being on the order of a few kilometers to a few tens of square kilometers, then that older technology, that watershed scale approach to mapping soil thickness, has proven to work quite well. So this was our essentially the trip I've taken as a geomorphologist was to start off essentially at that watershed scale, small watershed scale, and then in talking with system modelers and learning that the kind of uniformity that's assumed across the land surface globally, I decided to try to take that technology that's applied to the 30-meter resolution and make it global. So one can go back to the original papers that apply these techniques at 30-meter resolution and even higher. So in that original 2009 paper that I described, that was applied to LiDAR data sets, so 1-meter resolution application of those things. I have to share codes that can take in. So I have codes that take in a point-wise data set for soil thickness and spit out a spatially complete map given EM, that's all. And that can be done at any resolution effectively.
Su Liang's hand has been up, so I'm going to unmute Su Liang. Go ahead, Su. Hello. Go ahead, Sue. Hello, Su Liang. You're unmuted. Okay, not sure she is. Sorry that the mistake. Oh, that was a mistake. Sorry about that. Okay, I'm gonna mute you again. Any more questions? Or comments? Okay, if no more questions, comments, it's past 4 o'clock, and we can conclude here. We have a great deal to think about. There's so many great ideas and data sets now. I think these 4 seminar series right now gave us a lot of ideas, and we're going to do next during the next 2 weeks of a break. The last one will be May 30th, but before then we have 2 weeks of break, and we're going to try to write up some outlines, and then we can present those outlines at our last meeting on the synthesis paper, on the possible approaches, on all these ideas presented so far. And again, if you would like to be involved and not yet, send me an email to be included in future communications. If no more questions or comments, we'll say goodbye and see you May 30th, I believe. Yes. Which is the morning, it's a Tuesday, 11 a.m. in the morning. Thank you, everyone. And thank you, Liz. Goodbye.